Okay, thank you very much. Thank you for having me here, Dara and Bruce. It's great to be here. That's my first conference to social science. I hope it's not the last one. Okay. How many of you have heard of free energy? Oh, a lot of people, that's good. How many of you have heard of thermodynamics? Oh, it's fantastic. So we can save a lot of introduction. So I call myself a thermodynamicist is because I try to apply thermodynamics to all problems. So last Friday, I organized a workshop with 40 people from 18 different departments. Try to use what we do to solve all kinds of problems. I hope my discussion will be interesting to you. So maybe I come back to you guys in the future, collaborate together. All right. So let's talk about what the thermodynamics is. Thermodynamics is a language for systems. So you describe a system, you can define any system. It's to study. You can define brain. That's what one of our projects have. This social here is about a person, right? Society. So you can define a virtual system too, right? Black holes, for example. Okay. So when you talk about the thermodynamics, you're going to talk about the first law. That means how the system interacts with the outside. You have to have energy conservation. You cannot create energy. You cannot destroy energy. Energy is conserved. That's the first law. And if you do this kind of exchange interaction, the system is going to react. That's second law. Okay? You're going to have internal processes. That process will produce entropy. That's called entropy production. There are many fields use the second law. Okay? So if you want to describe this kind of observations, you're going to do measurements. These are observations. Observations basically are the derivatives of the free energy. Okay? So for free energy, you need two terms. You need energy and entropy. You put it together, you get a free energy. Okay? So basically, you think about a free energy, the energy minus the temperature times entropy. That's the free energy. That means you remove entropy from your energy, you get a free energy. Well, people invented that name many years ago. So what is empathy then? Right? Sorry, I had to go for defense in the morning, so I heard about a few minutes of Jana's talk in the morning. Do you remember her title, right? What are we measuring? Okay? You are measuring derivatives. Every measurement is a derivative of a system, of the free energy. That's what they do. So what empathy is today, of course, we talk about the psychological traits. It's fragmented, right? As we talked in the morning, and the different kind of aspects of it. And the AI is the same thing, right? AI is just a tool to understand complexity. So you always have different perspectives of the same problem because it's complex. It has so many faces of the same problem. So every face is correct. Nothing's wrong. Okay? It's just that everyone is incomplete. So if we want to put all together to make a complete picture, what should we do? We should start as a system. Okay? We should start the free energy of the system, then do the derivative of the free energy, but explain all the observations, then predict them. Okay? So that's my question. So I didn't copy that one from Jana because I had it already. So what exactly are we trying to measure? Okay. So empathy is complex. When we talk about empathy, we mix many things. We mix the process, we mix the attributes, so it's very hard to define. So as I mentioned, every definition is correct. It's one aspect that of complexity. There's nothing wrong. That means, again, it means it's so complex, one definition, not enough. You should put all of them together to solve our problem. So I would first say that empathy is not a trait. Okay, so that probably not agree with many of you here. So it's not a trait. What is it then? It's interaction. I think somebody mentioned already. It's interaction. The reason is because you don't have this kind of empathy by yourself. You have the empathy because you interact with somebody else. Okay? So it's a dynamic coupling between systems. So as I mentioned, you can define any system, right? You can define the whole room as a system. We have about 80 people. The 80 people, each of them is the subsystems. We interact with the subsystems, then we define how the whole system works. But we can also study just two people interaction, or three people interaction, or whole table interaction. Okay, so it's all kinds of things, depends on what you study. So it's relational, it's dynamic. It changes all the time. Okay, so it's from at least two systems, right? At least two systems. It evolves together. It doesn't become static, right? Because when you say something, that person responds something, they decide what to say next. Okay, it's not static. It's not because only that person's behavior. It's just two interactions. What you say will affect a lot on that empathy, all the interactions forward. So my proposal, okay, so I give a proposal on empathy from my point of view, from point of view of thermodynamics, okay? So my proposal is a quantifiable coupling between subsystems of a large system. So how do we quantify it, right? So think about this system, okay? It's a big system. As I said, it could be a black hole, right? It could be the room, could be in university, it could be your family. So there are a lot of subsystems in that big system. A, B, C, D, just an example. You have interaction among all of them, right? Between all of them. Even though you know that person is not here, you think about that person, even though that person is 1,000 miles away, you still have interactions. And the perspective is that can we use AI to unify all those interactions, okay, based on thermodynamics. So what is thermodynamics? I mentioned already, is the dynamics of this energy landscape. You think about this system has the energy, okay, have the landscape. That means this energy depends on people inside, depends on how we interact with each other, maybe it depends on what lunch we had, right, or breakfast we had. Okay, so all affected. So I'll give you an example. I have a colleague, my collaborator from paleoecology, Sarah Avery. We started Interact last year. So she was describing the challenges she has. She's trying to study the pollen, the fossil pollen 1,000 years ago, how it evolves as a function of time, how it evolves with the climate, how it evolves with people. Okay, so that means we have a system. What the system is the ecosystem. The lake she was studying, or the country, she's not in Africa. She just flew there Saturday, well, the meeting on Friday. And it's the whole system, right? The system has climate change, and has the people change, okay? Have the tree change, okay? They get subsystems, okay? Maybe you want to isolate the climate change, isolate the people change, or migration as your subsystem. And you have some configurations. Based on science, any system consists of configurations. Okay, those configurations are in the latent space. However, you measure something, try to find out what's behind it. That's about AI. So observables. So what do you observe? In her case, she dig up out this pollen from the lake. Then try to figure out how old these pollens are, the leaves, and try to figure out what do they belong to 1,000 years ago, and compare what do they have today. Okay, so it's a system, subsystem, configuration, and observables. So this can apply general to any system. Okay, all right. So that means to describe system use free energy, right? Because everything is energy and entropy. So if you describe this free energy, you're going to have a function, two terms. The left side F is the free energy. Okay, you got some mathematics, right? The left side is the free energy. Then E is the energy. S is entropy. T is temperature. So you can describe this system, and if you see that the curve you have here on the right side, you can have basins, right? So what does basins mean? That means it's stable. That's what you actually observe when it's stable. However, between the two basins, you're going to go with this barriers, right? That's called ridges with the barriers, okay? And if you put them together, you're going to observe something. Okay, so then try to take the observables back in the system, try to figure out what the free energy is, how the energy changes, how the temperature changes, how entropy changes. All right, so what do we actually measure? Okay, that's going back to my first, what I said at the beginning, everything you measure is the derivatives. Okay, what do you mean? Because when you measure something, you try to perturbate it, right? When you perturbate it, the energy changes. Okay, so you measure the change of the energy with respect to what you disturb it. But of course, sometimes you don't disturb. You cannot disturb a black hole there, right? But you can still measure what a black hole tells you. How do we measure it? I was talking with that lady in the morning. What do we measure? Everything we measure are waves. When I look at you, you see the waves from me. Okay? When I measure back from you, I see the waves from you too. So every communication is by waves. Waves are representation of energy. Okay? That's quantum mechanics. So that means what we measure, all the observers we measure are derivatives of energy. Okay? So you can calculate the derivative. First derivative gives you forces. So if that person working very strongly, you see, you get some pressure, right? The force is big. Okay. So second is that you look at the second derivative, is that how stable that person is. Is that a person so agitated by your staring? Okay. That's second derivative. So you put them together, you can see that the empathy is observable, right? We observe empathy when you talk with that person. So that means you are observing the derivatives of that interaction. That makes sense? All right. So that's what it means that if we want to describe it quantitatively, we have to get the free energy. We have the derivatives. First and second, I'm going to show you get to study derivatives too. Okay. So that means to give what is the entropy there, right? Because entropy is very important. That's second law. So if you look at this equation here, that's basically all the machine learning people do, all the statistical mechanics. You look at the probabilities. Probability of different things. And P is probability. Log of P is log of probability. You put them together, you get the entropy. Oh, should have minus sign there. Sorry, minus sign is missing. Should be minus because P log of P is minus and positive. Entropy is always positive. I must have made a change last night. Forgot that minus sign there. Okay. So that's what we typically do. That's called, if you do the AI, it's called cross entropy loss function. Okay. However, this number of configurations is huge in the system. So we cannot sample all of them. So we do coarse graining, cut in the middle. So instead of sample all of them, we sample some of them, right? Some of them, you get a probability, you get a P log of P. But then you realize that when you do the coarse graining, each configuration has some entropy inside because you sum them up from the bottom, right? That means you have to have two terms now to put the entropy. Again, I missed the minus sign there. Sorry about that. I have minus sign in the last part. That's good. At least I have one place correct. I have minus sign here. Okay. So that means you now have two terms. That means if you do machine learning, you have these two terms in one term. But today, in all the machine learning model, we only use one term, P log P. So that means today's machine learning is incomplete to count the entropy of a system. So that's my colleague at the mathematics. They invented a new term called cross zentropy. So what does zentropy mean? You have two terms here. One is the first term. That's the entropy of each configuration. Because when you interact with people, you have entropy. Then interaction has entropy, right? The interaction is P log P, but yourself is PK. Okay, so you have to put them together. So we had this model for a physical system back in 2008. During the COVID, I was giving talk about the online talk about our model. I said our model is not this and not that. There was one person from Buffalo. He said, "Oh, what do you call it zentropy?" So that's why I have zentropy. So Z is a partition function in statistical mechanics. So basically, use partition function, put the entropy together, so you get a complete entropy of the whole system. Okay, so then the mathematician said we should train our AI model use cross zentropy, so our entropy more accurate. So I have a cross zentropy loss function today. So the idea is that zentropy enables representation of uncertainty. What do you mean uncertainty? The SK is uncertainty. Because each configuration has its own entropy. That's uncertain about that person, about that event you have. So that's called uncertainty, quantification across scales. So what it means is that, so empathy requires two systems. Okay, of course you can say it's two subsystems, that's fine too. So you have A and B. So that means the constructive free energy has both A and B contributions inside. And then A is the observer, and B is the target. Okay, put them together, you see, now the empathy emerges not from A or from B alone. It's from the interactions, from the coupling. Okay, so that means the empathy is not a retreat of one person at all. Well, of course, it has contribution, okay, but not enough. Not enough with one person's contribution. Has to be two people. They have to interact with each other. Okay? All right, so that means we can do it now, right? First order derivative. That means how the target affects the observer. That's the first derivative. Okay. That means if that person is very excited or very sad, that's because the B put in a message into that person. Okay? So it shows the sensitivity of that person, A. And this is minimum requirement, has to respond. Okay? If that is equal to 0, that means it doesn't respond. Okay, okay, now the second derivative, second order. Now I see the B put its message out, affect A, then how A respond, right? Okay. So it's the curvature of a surface. Second derivative is coupling. So that means could be very little, doesn't change much. So it's very not sensitive, very weak. But it could be too strong. Get excited or get very depressed or get crazy. Okay? All right. So that means the third derivative is that how that the A will adapt, right? So you get a third derivative, the A will adapt it because see how the response is. B will change, A will change. So that's the third derivative of it. So is the context dependent and in terms of how systems behave near critical point. That's the instability we're talking about. Human-like empathy with a mechanical response is that we have to define now. So how to define the EMPs, okay? System with structured cross derivatives. So that means we have to be able to do the cross derivatives. The first order is response, the second order is the stability, the third one is adaptation. All right, so that means we can see that the human intelligence and AI intelligence, we have a physical, we can talk to each other, but the AI is representational. So dynamic is intrinsic because we talk to each other, we transfer information, but the AI is learned, and empathy is thermodynamics in human intelligence, but the AI is functional. Okay, so that means is that, again, it's the same mathematics, but even the physical realizations. So we developed this work with the mathematician, the new AI model called Zen. If you Google, that's the QR code there, or you can Google it. Get Zen. Basically, that we divide the system into configurations or subsystems first, then configurations. We learn all of them and put them back and predict it. We learn each configuration. We put them together, the derivatives. Then we calculate the consistency, make sure it's interpretable. That's very important. Then we can provide intrinsic AI safety too, because we put the big system into small systems. So it's not a monolistic model determines everything. All right. So I give another example for the geography. Again, you can see it's Zen Nong Li from the Department of Geography. It's about mental health, for example. So mental health can be affected by many factors. For example, neighbor, but the parks, or the casinos, right? So it's interesting that casino could play different roles. The last one is casino here. So casino could be either positive or negative. In the south side is not good, but in the central part is very good. So it's called a role reversal for different environment. Okay, so again, the derivative. So another one is go back to the one I started with the paleoecology. Again, Sarah, is that you observe one thing. You dig out from the lake, you found this leaf, the pollen. But it could have many interpretations. Okay, could all be correct. Okay, so it's really one observation, multiple interpretations. Okay, it's a distribution instead of just one variable. Okay, so that means the entropy view of this interpretation is that you learn the configuration is the latent mental state, the energy, mostly the entropy, then you can start to predict it. All right, so my last slide. My chair started this, I have 1 minute left. Okay, the idea is that empathy is derivatives. Okay, it's how to react. Okay. And then there's our model, it can learn the landscape, it can predict the derivatives accurately, because today's AI cannot do that. Why? Because today's AI is discrete. For discrete system, you cannot do derivatives well. And then we can social science is the inference over latent configurations. So latent configuration is what inside that person. Okay, we learn from that. The last one is empathy is coupling and uncertainty. Thank you very much. Thank you.
to you. We have time for one or two questions. Anyone have questions?
Hello, thank you so much for sharing your insights. I was wondering if you could give a little example on how you may define subsystems and like number of subsystems or the number of hierarchy in your example.
Okay, so from the science point of view, you can define anything as a system. Okay, you can define anything as a system to study. If you define a system, you have to understand how the system interacts with the outside. That's we call the boundary condition. Okay, but the key is that after you define that one, you learn what's inside that system based on the behaviors. Behaviors are the derivatives, right? For the derivatives integration, you will find the system behavior. Then you learn what's the latent space of that observation you have. We did for science, but haven't done for the human yet. I'm working with the people, if you're interested.
Okay, one more question.
I think mostly clarification to get clearer. So what units are you thinking of empathy? Are these in joules? Or tell me a little more precisely what a measurement, or give me coupling on uncertainty is a description. Can you give me a definition?
You can normalize it to anything you want. So for example,
so it could be joules, it could be number of people on a hillside.
Absolutely.
It could be milligrams of ink in my pen is also empathy?
Absolutely. So what happens is that when we did in our physical science, of course, we know exactly what it is, we can measure it. But for example, how do you define temperature of data? How do you define temperature of an image? You can normalize it. Okay? So you start with 1, then you go to 2, 3. You can normalize to the values you want to reproduce your data. So for example, for entropy itself, in our case, it's joule per mole per Kelvin. But in the information, it's normalized. It's known unit. Information entropy has no unit. It's P log P because entropy is divided by KB. So it's no unit. So you can do that. So you can do the normalizations the way you want to describe a problem. But the derivatives is independent of how you select your units. Carol?
All right.
Real quick. So, I mean, this is really interesting. Like, it sounds like you're essentially arguing empathy as sort of substrate neutral. It's all about the functional relation between interacting systems. I mean, that does connect to interesting work in psychology on emotion regulation and interpersonal emotion regulation. I can't say I've ever heard building off of that question we just heard, seems like you're really leaning into hardcore functionalism, basically. And is there any value in the substrate at all? Because in some ways, some of the crux of the AI empathy debate is all about the fact that the substrate mattering so much.
That's a great question. I don't think I have a full answer to that question yet, because in my domain, we have exact unit. We know what you measure, okay? But when we do for example, we do the image classification and the language classification in our paper, just published at the PNS, is that we just normalize it. We just normalize the value. But you see, it doesn't matter how you normalize it, your derivatives doesn't change. Because both E and S both normalized, derivative doesn't change. So normalization does not affect the derivatives. That's the observation. Mathematically show that too. Yeah.
All right. Thanks, Hikui.
Thank you very much. Thank you, everyone.